Welcome to the NYU Tandon School of Engineering. Let me start by thanking you for being here today. Thank you as well to Tandon Executive Dean Juan de Pablo, who also serves as NYU First Executive VP for Global Science and Technology, and Senior Vice Dean Ari Odell for their support, and to my own Department of Electrical and Computer Engineering for hosting the seminar series in Modern Artificial Intelligence. I launched this series 7 years ago, and it has been among the greatest pleasures of my career to see it evolve into a significant event in the AI world. Those of you who know me or who have been to any of the seminars know that I like to collect interesting quotes. In light of today's presentation, I've been thinking about autonomy, and I came across this from a writer named Daniel Pink. He believes that what truly drives us as intelligent, creative people is our deep-seated need for three things: autonomy, mastery, and purpose. We are all here with a clear purpose to keep abreast of the influential research ideas of today that can have a major impact tomorrow. And as is true for all of our speakers, we'll be hearing from someone with an impressive mastery of his topic, which includes the development of methodologies for the analysis, design, and control of autonomous systems, with an emphasis on self-driving cars, autonomous aerospace vehicles, and future mobility systems. Let me tell you a little bit more about him. Dr. Marco Pavona is currently an associate professor of aeronautics and astronautics at Stanford University, where he directs the Autonomous Systems Laboratory and the Center for Automotive Research. He also leads autonomous vehicle research at NVIDIA. Before joining Stanford, he was a research technologist with the robotics sections at the NASA Jet Propulsion Laboratory. He received a PhD degree in aeronautics and astronautics from MIT in 2010. Today, Marco will be discussing foundation models for autonomous driving, and I love his description of these models as being trained on vast and diverse data encompassing the human experience. So without further ado, please join me in welcoming Marco Pavona.
Thank you very much for the kind introduction. It's a pleasure to be here. So what I'd like to do in this talk is to discuss how recent advances from the field of foundation models, for example, vision language models, large language models, are providing key opportunities to rethink how we build autonomous vehicles and robotic systems more broadly. Now, the premise of this talk is that, well, as everybody knows, generative AI is changing the way that we work and we seek out knowledge. For example, models can write that code for us, as depicted here on the left. An emergence of such capabilities is so profoundly revolutionary that some people refer to it as the iPhone moment of AI. But broadly speaking, the main cause of such an acceleration has been the advent of foundation models, which have shifted us from a paradigm of machine learning for specialized tasks toward a paradigm of general knowledge acquisition. And to be more specific, by foundation model, I mean a model that has been trained on raw data, typically at internet scale and in a self-supervised fashion. And it can be then adapted to a wide range of downstream tasks. Typical foundation models include large language models, vision language models, video generation models, and NVIDIA actually has a catalog of the foundation models on its website that you can play with to just get an appreciation of the possibilities. Now, we're not quite there yet at one gigantic model that can ingest any data modality and that can be adapted to any downstream task. But this general idea of training on very broad data and then adapting the model to specialized tasks has proven useful in a number of settings, to the point that oftentimes when you play with these models, you are left with the exclamation, wow, I didn't even know that such a model could do that. So it's empty to say AI, and in particular generative AI, makes everything better. So let's apply it to autonomous vehicles and robotics. Well, before applying foundation models to AV development, it is important to contextualize in what ways foundation models can boost AV performance and safety. We don't just want to jump on the bandwagon because there is a lot of hype around foundation models. And indeed, the AV technology is quite mature, with advanced driver assistance systems being productized as we speak, And companies such as Waymo testing and actually offering robotaxi services in a number of cities in the United States, for example, San Francisco. And this has been powered by the judicious incorporation of specialist machine learning models within an AV stack. However, these models still miss the mark when exposed to the long tail of events that an autonomous vehicle might face during operation. For example, new deployment domains, optical illusions, like, for example, a truck that is transporting traffic lights, which could be confused by actual traffic lights. Or I don't even know what we have here on the bottom right, where there is a giant mignon in the middle of the road, and somehow the vehicle should reason whether it is safe to push through it and proceed. So these are all cases that require higher level semantic reasoning for generalization, and they're still very difficult to address with traditional AV technologies. Now, at this point, it's useful to wonder how humans navigate the long tail of events. Well, as humans, we bring in a lifetime of general experiences beyond only driving. And this basically provides a strong contextual and semantic understanding to reason about weird situations. Analogously, the hypothesis that the foundation models, which have been trained on broad data, both from the driving domain, but crucially also from the non-driving domain, provide an opportunity to bring this multiple lifetime of experiences to the task of driving, in some way replicating the contextual and semantic skills of a human. At least this is the hypothesis. Now, the question that we will be exploring in this talk is how can we access this generalist experience for the purposes of autonomous driving, and are these potential benefits actually materialized, and how do we quantify those? Well, first of all, I'd like to point out that the way that foundation models can impact AV development is very broad. As I'll discuss in the rest of the talk, foundation models can empower several aspects of AV design and deployment, from offline development processes such as auto-labeling pipelines, sensor and traffic simulation, and scenario generation, all the way to the onboard stack, either by enabling new end-to-end architectures, for example, or improving existing architectures, for example, through monitors. And of course, safety is a key consideration. Of course, several people are a bit uneasy in using, say, a large language model in a safety critical system. For example, everybody is familiar by now with the issue of hallucinations. But what I will argue in the talk is that actually we have a number of tools at our disposal to keep the AI in check. But at the same time, foundation models also provide opportunities to increase the safety of an autonomous vehicle, for example, by allowing the design of more powerful runtime monitors. So what I'll do in the rest of the talk will be to first start with some general considerations on how we build foundation models specifically for the task of autonomous driving. Then I will provide a few examples of how we are currently infusing foundation models in a V program, both in terms of offline development processes and the onboard stack. And then I will conclude the talk with a discussion about safety considerations. Good. All right. So let's dive into the topic of building foundation models for autonomous vehicles. Now, focusing in particular on their core design choices. And at a high level, there are three core choices: data, model, and training tasks. A foundation model can generally take diverse inputs, and actually this is one of the advantages of foundation models. Particular for autonomous vehicles, we focus on multi-sensor data, for example, camera and LiDARs, vectorized data, for example, maps, or even intermediate representations such as BEV features, for example, for offline models. On the model front, backbone choices include autoregressive models popular in the large language model setting, and the diffusion models that are popular in the video generation setting. And finally, we split the training into pre-training and fine-tuning tasks. For pre-training, we aim at leveraging unsupervised tasks that can scale to internet scale through self-supervision. What are the modalities that abound on internet, language, and video? So one key pre-training task is that of language generation, and another key pre-training task is that of video generation, with the hypothesis that language generation provides a sort of reasoning capability into the model, while visual generation is a good pre-training task to build very strong, powerful visual representations on top of which you can then stand up a planning head. Then we fine-tune the models with various AV-specific tasks. For example, trajectory generation if you want to control a robot. Now, multimodal large language models pre-trained on the task of language prediction represent a prominent class of foundation models for AV and robotics applications. Since the model is pre-trained on internet scale language data, it has strong capacity for common sense reasoning. Here I show just one example from our work where we use large language model more as a sort of a co-pilot to help human drivers to understand confusing situations. So for example, this is a road in Mexico. And as you can see, there are some confusing arrows that are telling traffic to actually move on the opposing lane. So here, the concept is that you would ask the AI in the cabin, in the cockpit, so what am I supposed to do here? So we develop a model that allows you to have this kind of interactions. The model is called LADA. And here you see its response. Oops. So we ask LADA, so what's happening here? And then the model responds, please follow the arrows and switch to the opposing lane when safe to avoid oncoming traffic is the indicated traffic arrangement. This is indeed a legal traffic arrangement. And I don't know exactly the logic of it, but I think it's to allow for the trucks that are going downhill to use the internal part of the turn to have a little bit wider space for the turn. I don't know exactly what it is the case, but it was quite remarkable that actually the model can tell you exactly what to do here. Now, this is just one example. We'll come back to how we use the multimodal large language models as part of an autonomy stack later, and also the observation we've seen in terms of tangible improvements in performance. Here instead, I want to focus a bit more time on another class of foundation models referred to as video generation models, where the task is that of video generation. Video generation models are comparatively more recent than large language models, and they become popular since last year with the advent of Sora from OpenAI. As the name suggests, for pre-training, the aim is to predict multiple frames of videos. And as an example of a video generation model for autonomous driving, here I present one of our latest token-based multi-view video generation models. Our work is inspired by Gaia 1, which is a work from a company called Wave, whereby the idea is to turn the video generation problem into a conditional sequence prediction task, very similar to what is done with large language models. But we make many innovations with respect to the Gaia 1 work, in particular in terms of generating multiple views of a video, essentially replicating the fact that on an autonomous car, you have multiple cameras. So here are some examples of videos being generated by the model conditioned on a text prompt. For example, generate a wintry day in the city with a car driving past a snowman built near a bus stop. So here you see 3 videos, and you see how they are nicely synchronized. For example, the car on the right is also getting in the view of the center camera. So these are all AI generated. This is not a video. This video never existed. Something here, similar here. Now you don't have to stop to 3 videos. You can go to 6 videos. So for example, this is an AI generated video of driving on the highway or on the parking lot. Of course, video generation is still a relatively new technology. It is not perfect yet. So for example, I will point your attention to the box in green. You'll see that something funny happens. You see that the motorbike appears and then disappears. Not great if you want to use this either as a simulator or as a sort of data for generator data for training. Of course, the models have improved substantially, including how to address the issue of object permanence. And we'll come back later to how we might address these issues later on. Now, my point here is that there is foundation models is a broad term. There is a large family of foundation models you can play with. The jury is still out in terms of which foundation model is best for what. I would say that multimodal language models being pre-trained on language generation have the possibility of becoming the ultimate reasoner, while video generation models being pre-trained on the task of video prediction have the promise of becoming the ultimate way to generate very strong visual representations on top of which you can build a planning head. And they're not like mutually exclusive. You can actually combine the two, and I will come back to this topic later on a bit. All right, so let's turn our attention to how we can use foundation models as part of an AV program, starting from offline processes. And here, I'm just going to give a few examples. There are many more that I could give. Now, simulation is the holy grail in the field of robotics and autonomous vehicles. Of course, if you had a good simulator, the speed at which we could develop an autonomous systems will be greatly accelerated. Now, near field representations such as nerves have emerged as an extremely powerful tool for scene representation and reconstruction. So here I show a video of our recent work, EmberNerve, that can decompose a complex scene into its static background, dynamic objects, as well as estimated scene flow, thereby providing scene reconstruction and representation in 4D. And all of this is achieved solely through self-supervision, that is, without relying on any external labels provided by humans. And when this is useful is that it can be used for simulation purposes in a way that dramatically decreases the sim to real gap. So for example, on the top row, I'm showing you a real camera log, so a video that has been acquired by a vehicle. And at the bottom, I show the same video, but reconstructed from a novel viewpoint. So think of it of a sort of a simulation whereby we perturb the trajectory that we use to gather the video. And what you see is that you obtain sensor readings that are extremely realistic. I mean, I would challenge you to tell which video is real and which one has been generated, reconstructed with a neural network. Of course, we're doing reconstruction. So at some point, if you change your viewpoint too much, then the underlying neural network can't generalize anymore, and you start seeing artifacts. We'll come back to that later. But at least locally, it represents a very good way to do simulation. And you can reconstruct not just camera images, but also LiDAR point clouds. So this drastically reduces one of the notorious issues with simulation, that is that of scene to real gap from a sensory point of view. But a caveat here is that all the agents in the scene, pedestrians, cars and so on, are being replayed. So they're not really reactive to what the autonomous vehicle under test is doing in the simulation. So to fully close the loop in the simulation, we need to have a traffic model that can control the behaviors of all these agents. And accordingly, my group has conducted a lot of research on traffic simulation, pushing the state of the art in terms of realism, diversity, and controllability. But while we're now in a position to produce high fidelity behaviors for humans in a simulation, creating or instantiating new simulation scenarios is still very complicated. Sure, you can easily create scenarios where a car drives on a highway, but that is not really interesting. It's not really informative. You want essentially to generate corner cases, the stress test a system. And this is where a setting where foundation models can boost our existing capabilities. Specifically, we have explored how large language models can enable a new and intuitive interface to control the generation of simulation scenarios. With our recent work, LCT-Gen, we are able to not only control the evolution, but also the initialization of a simulation scenario by using straightforward natural language descriptions. So here, just I'm showing you snapshots of scenarios that are initialized through text descriptions. One thing I would like to notice is, for example, actually I have to stay close to the microphone, is here, you see there is a blue vehicle behind the red vehicle. We ask the model to create a scenario where we accelerate all of the vehicles. And then the model is intelligent enough to move the blue vehicle to the other lane, because if you were to speed up everybody, the blue vehicle, if it stayed in the same lane of the red vehicle, would rear-end the red vehicle. Where this gets particularly useful is now you can mine all the police reports that have been filed about crashes worldwide and use them in a way to initialize new simulation scenarios. It is important because it gives a sense of plausibility to the scenarios that you generate. When you generate stress testing scenarios, there is always a question of, is this realistic enough? It's easy to generate a particular adversarial scenario, but you have to thread the balance between adversarial and what possibly can happen. Grounding the generation into police reports is a good way to endow the procedure with some notion of plausibility. Of course, the police reports are just scribbles. So basically what we do with this technology is to turn those scribbles, add a bit of generative AI to recreate all the surrounding environment in a plausible way, and then recreate all crashes that have been stored in a NHTSA siren database at scale with a minimal supervision. And to give you a little bit more insight, LTC Gen works by first converting a given scenario prompt into a structural representation, an example of which is represented in the bottom right corner in purple. And then this representation is taken as input into a map retrieval framework that selects the best fitting road layout from a map of possible road layouts. And then as well as a motion generation that then initialize the position of all the agents and also predicts their trajectories for the next 5 seconds. Now, what is useful, there are still some caveats in the sense that it's quite finicky, for example, to specify metric quantities by just using language, like, for example, what exactly you want to have your agent to be instantiated. So accordingly, we made an improvement to LCT Gen, which we call ProSim, which is a much more flexible, promptable traffic simulator, whereby you can provide as conditioning input goal points or sketches of trajectories, text description, and what have you. So this is actually a tool that we are currently using at NVIDIA for scenario generation. Now, putting together everything together, we can combine scene reconstruction with the capability of generating targeted scenarios through language guidance to simultaneously simulate a sensor and the human agent's behaviors in novel targeted ways. For example, here we want to test an AV stack on a long tail scenario whereby a vehicle shows ignorance of a stop sign. The video on the top is a video that actually happened, it's a real video. And there is a vehicle on the left there that is stopping at the stop sign. So it's doing the right thing. So now we're asking the AI model to give us a new simulation scenario whereby the same vehicle on the top now acts recklessly. And so here you see the result of combining all these new technologies. You've had that the AI model removes the vehicle from the scene, reinserted it, and in this case, interprets driving recklessly as not stopping at a stop sign, and you had a vehicle that speeds through. The video on the bottom is not the real one, it's the one that is generated by our scenario generation pipeline. All of this to say that through a combination of technologies that span neural reconstruction, generative simulation, language-guided guidance for scenario conditioning, and so on, we're much closer to use a simulation for AV development for real. I mean, of course, simulation has been used for a while, but it was mostly in the most basic instantiation where you do log replay. So you just replay a given trajectory. Now we can do much more, both from the point of view of testing and also training. Now, one more thing I'd like to say for simulation is that I showed you before how reconstruction is very useful as a tool to represent a scene in a way that, at least from a sensory standpoint, is very accurate. But reconstruction, by its name, reconstructs. So if you are trying to then perturb the scene too far away from the trajectory that was used in order to record the scenario, then the reconstruction process starts to break down. And in any case, you can't really scale to completely new scenes because you don't have, a recorded trajectory that you can use for reconstruction. Here is an example whereby we have a vehicle that is now performing a U-turn that is completely different from the trajectory that was used to record the drive. And now you see that the neural reconstruction-based simulator here is starting breaking down with a mess of artifacts and so on. It's a minor miracle that the end-to-end policy here is still working, even though you have all that stuff, or maybe not. But anyway, so the point here is that these are the type of artifacts that you get if you move too far away from the scene that was used for reconstructing the simulation rollout. Well, I talked before about video generation models. So it seems, logical to say, well, if you really want to endow the procedure with more generalization capabilities, let's use a video generation model. But as I said before, video generation models still have the issue of artifacts. They're improving, but still the question of their physical accuracy is there. So we recently explored the question of how we can endow generalization capabilities in reconstruction pipelines through a work called Dream Drive that actually will be presented at ICRA later this year. So the idea is to bring together the strong generalization capabilities of a video generation model with the geometric consistency of a neural reconstruction pipeline within a unified framework that essentially gets the best of both worlds. Specifically, the process starts with initial context frame. For example, here, a picture of a road in Tokyo, Japan. Then we use a video foundation model to generate a video from that initial frame. But here you see that there are some artifacts. So for example, you see that to say close to the mic, you see that the color of the grass is changing erratically from green to brown. And maybe in this case, that is not too bad, but this is to say that these video generation models sometimes they still give weird things. So what we do is then to feed this video into a neural reconstruction method to produce a 4D spatiotemporal representation of the scene. And this kind of neural reconstruction process enforces geometrical and temporal consistency by its very nature. And finally, an ego vehicle can be placed within this world and drive through it in a closed loop. So importantly, here we ground the simulation in realism in two ways. First, because we have a context frame, or we could also have text. But most importantly, we enforce geometric consistency through reconstructing the scenario with a neural reconstruction pipeline. There are many other ways to bring together neural reconstruction with a generative simulation. So this is just one example, but I'm kind of excited about the idea of bringing together the best of both worlds with respect to these two separate literatures. Okay, so let's move on then to the task of online driving, so onboard driving. I discussed before that foundation models hold a promise to allow us to drive better through improved generalization. But the question is, so it makes sense at a high level, I hope. But the question is, do we have evidence for that? So earlier last year, we started exploring this hypothesis through a work that we call Agent Driver, where essentially we set up an embodied agent that is a large language model that calls on demand different driving capabilities, such as trajectory forecasting or detection or segmentation and so on and so forth. So basically, this kind of embodied agent has multiple modules that you can call on demand through a text interface. This is not how you would architect an autonomous vehicle, of course. For one, is from a latency standpoint, as you can imagine, this approach is not great. But here the idea was more to do a science experiment to see whether foundation models can really realize this vision of bringing internet scale knowledge to the task of driving. And the most important plot is the one in the bottom left. So on the x-axis, I show the percentage of AV-specific data that is used to fine-tune this large language model embodied agent. And on the y-axis, I show a couple of driving quality metrics, essentially how well we can track a lane and to what extent we stay out of unsafe conditions. And we compare performance with respect to the best available autonomous driving model in the academic community, uni-AD at the time. And so what you can see is that with just 1% of AV-specific data, the LLM embodied agent, so agent driver, can achieve performance that is better than the best model available in the open community. And of course, the performance increases as you expose the model to additional AV-specific data. So it's kind of interesting. With just 1% of specific data, you already beat the strongest baseline in the community. And there is no black magic here. So this is just validating the hypothesis that actually agent driver purposely bring this kind of internet scale knowledge into the task of driving. So you don't need that much additional knowledge. So, and Anna, this goes back a little bit to the discussion we were having before about how we can build this kind of generalist representation of knowledge so that you can get away with much less AV-specific data. And we saw similar interesting results by using vision language models in a related work, which is called VLM, that is called Dolphin. Okay, so it seems there is promise in terms of using large language models, vision language models, foundation models in general for the task of driving. So then the question is, how do we best use or inject these foundation models into NAV architecture? And so this brings me to one of my favorite topics, that is that of system architecting. And I had the pleasure to discuss this topic at length, for example, with ERS in the recent past. So in general, and simplifying things a bit, these stacks are classically architected in a very modular way, with the key modules being, for example, detection, tracking, prediction, planning, control, and many more, for good reasons. So such a modular architecture is highly explainable, introspectable, debuggable, but it also has downsides. It cannot be end-to-end optimized, so arguably you might leave some performance on the table, and it gives rise to significant integration challenges. So this prompted in about 10 years ago, early 2015 or so, to start exploring end-to-end architectures. And its most basic instantiation, which I refer to as a monolithic end-to-end architecture, essentially you have a very large model, typically a neural network that maps sensory inputs into control actions. And this has a lot of promise. So basically the model can be end-to-end optimized. So notionally, the ceiling of performance is much higher with respect to a modular architecture, but it has its own challenges. For example, building a safety case for such an architecture is hard and is much less reusable. But in the past few years, thanks in part to advances in the field of differentiable optimization, a new paradigm has been emerging, which I refer to as differential and modular AV architectures, whereby you have an architecture that still has some modules or some components, but they can be end-to-end optimized. So if we are then hopeful about modular and differentiable AV architecture, then we have to understand, okay, which modules do we want to have in this modular and differentiable architecture, and how do we make them differentiable? And here the design space is huge, and essentially has three main dimensions. The choice of modules, which modules do we want to have represented? Do we want to have an occupancy prediction module, for example? How do we represent the information? For example, from the point of view of mapping, do we represent information through BVE map, or maybe in a more vectorized way through polylines and polygons? And another dimension that is sometimes overlooked is that of the dependencies among modules. For example, should the occupancy prediction explicitly depend on motion prediction? Maybe yes, maybe no. So to systematically explore the huge design space along all three dimensions, in a paper that we presented last year at the CDPR, we proposed a computational graph paradigm to model the general driving task. And through this paradigm, we can reason about the different architectural choices in terms of the necessity of a given module, its placement within the architecture, and what specific type of representation to use. Quite excited about this work, as it provides one of the very first tools to systematically explore the design space for AV architectures or for robotics architectures more broadly. So thanks to this paradigm, we were able to explore and evaluate many different architectures. And our key observation is interesting and perhaps even somewhat surprising. So it turns out that one of the simplest possible designs, namely a fully parallelized AV architecture, appeared to be the best one in terms of both performance and efficiency. So briefly, this architecture, which we refer to as a paradrive, entails a transformer that takes multi-camera images as inputs and produces outputs for 4 key tasks in parallel: mapping, motion prediction, occupancy prediction, and motion planning. Importantly, paradrive follows the principle of train heavy and infer light. In offline training, all parallel heads are necessary and crucial, as the co-training of the different heads ensures that the learned features implicitly encode the task of mapping, of motion prediction, and occupancy prediction, which then yields strong planning performance. But at inference time, we only exercise the motion planning head, the one that produces the action or the trajectory, which provides significant computational advantages. So we show, again, comparing this architecture with respect to the past models in the academic community at the time. We show that this architecture is both safer and significantly faster because we only exercise one part of the architecture online. And interestingly, this architecture addresses quite directly one of the issues of end-to-end models, in the sense that it still retains some form of introspection, in the sense that online, at your discretion, you can still exercise some of the other heads, for example, mapping and motion prediction, to get more insights about what the system is thinking. But maybe you can do that at a much lower frequency, maybe at 2 Hertz or 3 Hertz, and then use these additional signals, for example, as a consistency checks as part of a broader architecture where you also have a parallel algorithmic pipeline to give the full system diversity and thereby stronger safety guarantees. So encouraged by these preliminary results, we further extended this archetype with 3 core lessons from the design of foundation models, which include the use of a scalable self-supervised losses, such as language prediction and the video prediction. So we're coming back to the topic of large language model and video prediction models. A tokens in, tokens out autoregressive transformer backbone, which itself can be trained from scratch or can be a pre-trained large language model. And then use of internet pre-trained foundation models for tokenization. And to evaluate this foundation model empowered parallel architecture, we implemented a version whereby we have as an auxiliary task that of a video generation. Of course, we don't care about generating video when we drive, and accordingly, we don't generate video when we drive. This is something that we only do at the training time to force the model to acquire a strong visual representation of the environment. So here I show the model driving in our in-house simulator that uses a neural reconstruction, in this case, performing unprotected left turn. And encouraged by these results, then we tested this architecture on the road. So here, close to headquarters. And basically, this architecture at a fraction of the cost, at a fraction of the development cost, with a fraction of the data that is typically needed to drive, is able to drive satisfactorily without safety disengagements for relatively long stretches of time. So view this as essentially end-to-end 2.0 in a way, where the architecture is end-to-end, but we have some notional modularity to better shape the latent representations. We further experimented with using an internet pre-trained vision language model as the core autoregressive backbone. And immediately we see improvements in trajectory generation performance shown on the right, as the pre-trained large language model achieves lower trajectory error compared to the same architecture that was trained from scratch and converges faster. So this is really evidence that actually these pre-trained large language models really help for the task of driving. So it's not hype, it's not hypothesis. Now we have quantitative evidence that is actually motivating us to keep investing on this type of architectures. And so basically, I would say that this type of results corroborate the hypothesis that language pre-training synergizes well with the task of driving, which maybe is not too surprising in the sense that with language pre-training, you're exposing the model to all possible logical pathways. And driving is, pattern matching and a logical pathway in a way. We conducted closed loop experiments with this architecture as well in our simulator. And here we show that, for example, with this architecture, we can basically zero shot handle fairly complicated situations, like, for example, navigated through construction zones without any particularly dedicated accounting of how to reason about these complicated scenes. So looking towards the future, I'm quite excited about the potential for a unification across these self-supervised modalities, so both video generation and language generation. Language generation actually could be optionally exercised at the inference time, for example, to help with debugging, or again, to provide consistency checks with respect to parallel algorithmic pipeline. One thing that I'm particularly interested in is to make this model increasingly reasoner's model. Many of you probably are familiar with the DeepSeek. So we're actually working quite hard on setting up meta action and reasoning traces data that are causally correlated with the trajectory generation, and use this kind of a rich data set both for post-training and then for RL fine-tuning. So stay tuned for more, probably in a couple of months. All right, last topic, safety. It's not the safety last, but not the least, in the sense that it's probably the most important topic. Of course, there are a lot of concerns in the community about how do we field confidently these models. And these are all valid concerns, but it's important to recognize that foundation models are not black magic. I mean, they are large models, but the automotive community in particular has a long history of confidently deploying data-driven models. And accordingly, we have many tools to keep the AI in check. And broadly, we have 3 ways to guardrailing an AI system for safety critical applications. Design time guardrails. So these are steps we take in the design and training of a foundation model-based stacks, for example, ensuring that the data set contains only safe behaviors, or architecting your system in a way that you have enough diversity in the system, for example, so additional parallel algorithmic pipeline to make sure that you don't have common causes of failure. Runtime guardrails. So these are steps you take at runtime to monitor your system, for example, the input level, to make sure that your system is not operating out of distribution, at the output level, for example, through temporal consistency checks, and through arbitrators that try to give control back to contingency planner if we perceive that the end-to-end model is driving erratically. And of course, validation guidelines to make sure that before we deploy the system for real, we meet rigorously defined safety KPIs. I could spend the entire talk discussing these topics, and here I provide some references you can look at if you're interested. But even better, at the last GTC conference, Jensen Huang, who is the CEO of NVIDIA, announced NVIDIA Halos, which is a comprehensive safety system for physical AI safety that incorporates several of our research results on the topic of AI safety. So to learn more, you can watch the recordings of our AV Safety Day that we had a couple of weeks ago, or just email me and I'll be happy to share the 180 slides. But what I want to do here instead is to discuss in some details the opportunities offered by foundation models to improve the safety of a stack, particularly in the context of building better runtime monitors. So let me contextualize this a bit more. So here I'm showing you a display of a Tesla vehicle where you see that there are traffic lights that are spawned by truck, which doesn't make any sense. But it makes sense. So here we go back to the example I had at the beginning of the presentation where we actually have a truck that has traffic lights that are detected as real traffic lights, confusing the system. But here there is another example. By the way, I don't have anything against Tesla. I think they're pushing like amazing technologies out there. So here there is a stop sign that is printed on a billboard. And here there is an angry customer that complains that every time the vehicle goes by the billboard, the vehicle stops because it interprets that stop sign as a legal stop sign. So my point here is that you can't say that in any of these examples, the autopilot is doing something wrong in the sense that the detector is correctly detecting a stop sign and accordingly is stopping the vehicle. So I refer to these anomalies as semantic anomalies, anomalies that are due to a highly unusual combination of in-distribution events. And my claim is that all that the vehicle needs in order to reason better about the semantic anomalies is a bit more contextual semantic understanding of a scene. So for that, I mean, as the main philosophy behind this talk, we try to turn to foundation models, in particular large language models. So we have recreated the same example of the Tesla, where we have a truck that is carrying a traffic light and the vehicle stops on the highway. So we use an open vocabulary object detector to parse the different elements in the scene, including that there is a truck carrying a traffic light. And we use this information together with some additional prompts to basically tell the large language model what it means to be a runtime monitor, to ask the LLM whether this is a scenario where we should be concerned about. And the output is interesting. So basically, the model correctly identifies that a tree is not a cause for alarm, but a truck carrying a traffic light should be considered as an anomaly. And it also gives an explanation about this anomaly. It says, to the question, can we drive safely here? It replies, no, this could deceive the vehicle into interpreting the traffic light as a legal traffic signal. So it seems promising. But of course, running a full-blown large language model at runtime as a runtime monitors may be prohibitive. Runtime monitors are additional pieces of software, so they should be as lightweight as possible. So to address this challenge, then we consider the intuition that oftentimes detecting if something is anomalous is much easier than thinking about how to behave through that anomaly. And for detecting if something is anomalous, we can just leverage the large language model embeddings, which is much faster than the full autoregressive generation of text. So what we do was to explore this idea by using the LLM encoder to compute embeddings from the robot's prior experience in nominal situations. And these embeddings are then stored into a vector database. And then for new observations that come in online, we can compare these embeddings against the database to quickly observe if a situation is anomalous or not. And by using the LLM embeddings to do this computation, we can be very fast, but at the same time retain some notion of semantic reasoning to have a more nuanced characterization of a scene. And then if an anomalous situation is detected, then we can query a full-blown LLM to reason in terms of which contingency plans we should enact. So this is how all this works. So on the left, we have a baseline with a no LLM reasoner. So this is all in Carla. We have a stop on the billboard. And mistakenly, the system decides to stop. Here with our system, ESOP, we've represented the RSS last year and actually won the best paper award. The system detects that there is an anomaly, and then it queries an LLM, GPT 3.5 in this case, to see whether they should continue. And the reasoner says, yes, there is no cause of alarm. A stop on a billboard is not. a cause for alarm. So let's see a little bit better how this works. So here we have the LLM embeddings that are used for anomaly detection. And we can do this very, very quickly in a matter of a few milliseconds. So we can run it at 20 Hertz on an NVIDIA Jetson. And once an anomaly is detected, we query GPT 3.5 to reason about what to do next. In the specific setup here, GPT 3.5 incur a delay of about 2-3 seconds. So all of this is orchestrated through a model predictive control scheme that takes into account the delay that you would incur by querying a large language model so that it predictively generates always contingency plans that potentially slow down your dynamics to allow for the querying of the GPT model, similar to how humans drive. So typically when you drive, probably you don't pay much attention to the task of driving, but somehow your brain is constantly looking at anomalies. If there is something weird, then you slow down to buy yourself some time to think about what to do. So that's what this overall MPC architecture is doing. So, of course, it's just a qualitative demonstration. In the paper, we have a much more quantitative analysis in terms of true positive rates, false positive rates. You can see that actually for the data sets we looked at, we have a very high true positive rate. The false positive rate is medium. But importantly, this implies that we induce some level of conservatism. So we are erring on the side of caution, which is the thing that you should be doing. Of course, there are many things you can improve the system. For example, considering higher capacity models for slow reasoning would dramatically improve accuracy. For example, if you use GPT-4 instead of 3.5, but of course, you introduce more latency. So it's a little bit of a balance between the two. Here, we only reason about single frames. Of course, if you reason about multi-frame observations, you have a much better understanding of anomalies because some of them require temporal cues. One interesting thing to do here would be to reason about the uncertainty in the outputs of the foundation models to have a more nuanced assessments of anomalies. And here we use the models basically out of the box. Of course, you will get much better performance if you were to fine-tune them. Running a little bit out of time, so I will be quick here. We tested this framework on a real system to convince you that we can do it in real time. So this is a quadrotor that is tasked with landing on the box with the orange top. It's navigating through a cluttered environment. It's seeing for the first time a keyboard. This is something that is never seen, doesn't know if keyboard can shoot missiles. So it's detected as an anomaly. The large language model says, no, there is no reason to worry about it, keep going, and then it keeps going and keeps going, and then it lands on the box. If you're interested in this, in the topic of auto distribution, detection, runtime monitoring, contingency planning for robotics, we had sort of a survey paper, position paper on arXiv that tries to provide a taxonomy about all these problems. All right, so let me wrap it up. So what did we want to communicate in this talk is that foundation model might provide a quantum leap in terms of long-tail generalization. But now we have some evidence to this hypothesis. And second important concept is that even though foundation models are typically discussed in the context of the onboard stack, they might have many additional use cases, even more impact in the context of a full AV program. We saw, for example, some applications to simulation. Foundation models is a broad term. There are many different types, from a large language model, vision language model, video generation models, and they're largely complementary. And I see a future where many of these will be unified under one umbrella. In terms of how to use them as part of an AV, they can be used in multiple ways, either as part of the primary algorithmic backbone, or as an auxiliary algorithmic pipeline, for example, for runtime monitoring. And for safety, what I argued is that we have several tools to keep these models in check. But at the same time, these foundation models also provide new opportunities to make a stack safer, for example, through the development of more advanced runtime monitors. So with that, I'll thank my students at Stanford my colleagues at NVIDIA, in particular, those that are part of the AlphaMayo team, that is essentially the program within NVIDIA focused on end-to-end autonomous driving. Right. Thank you very much. Eugene.
Great talk. I really enjoyed the bit about foundation models at the end, and I was curious how you think about, in a world where your attack tells you one thing and the foundation model tells you another thing.
Wait, we're sorry, the
Your foundation model tells you one
Yes.
thing, and your vehicle stack, the sensor stack.
Yeah.
How do you think about those things being fused together?
Yeah, that's great. Actually, in the AV safety data that I mentioned, we had an entire session about how to fuse together the output of a more classical stack that essentially introduced diversity into the system with the output of the end-to-end model that is aimed at giving you more naturalistic driving, better driving in difficult situations. And so the challenge there is that the classical stack might hamstring the end-to-end stack because it is less powerful in a way. So the way we see it is that a classical stack doesn't really output the trajectories, because if you were to arbitrate that with those of an end-to-end model, how do you choose between the two, right? But we actually use them, we use these classical models to provide the physics-based guardrails. So essentially to provide a regions of the state space within which the end-to-end model is allowed to drive. And whenever the end-to-end model is producing trajectories that invalidate that region, then we give control back to the classical stack. Importantly, such a way to define a region of the state space within which the end-to-end stack is allowed to drive has to be calibratable. So how do you tune its sides? And the idea is that as you gain more experience with end-to-end model, then you keep basically increasing. And this is, I think, a promising way to do arbitration at the planner level. The other way you could do it would be, but then it wouldn't allow you to use an end-to-end stack anymore, is to do arbitration at the perception level. But then you will lose the potential offered by end-to-end model in terms of better driving. Concretely, the way we compute these physics-based guardrails is by using techniques from reachability theory. Some people might have concern that reachability might be over-conservative. Reachability is really a framework. Actually, it's not like an algorithm. So depending on how you tune it and how you calibrate it, you can get a lot of different behaviors, and that's basically what we're currently working on.
Very much.
But yeah, this is one of the hardest parts to develop a safety assurance case for an end-to-end system. On the other hand, it will be very hard to develop a safety assurance case if you don't rely on some other elements of your architecture that provides diversity, particularly for high levels of autonomy, in the sense that, maybe with tens of thousands of hours, you can validate an end-to-end stack for low L2 applications. But as you go to very high levels of autonomy, it requires millions of driving. And in particular, you will need to revalidate the stack every time you change the policy, right? Because you can no longer validate it piecewise. So you have to decompose your safety targets in order to be really practical. So I think this is probably one of the, at least for me, I come off from a control theoretical background, one of the most challenging but also interesting aspects of how we deploy end-to-end systems in practice. Sorry for the long answer, but it's one of my favorite topics. So I should probably include some slides in the future.
First of all, I was looking forward to the seminar. Thank you for this talk. So I was wanting to ask, did your team explore the ideas of liquid neural networks for regressional outputs? Just like you said, the classical stack hamstrings the stack you have right now because it doesn't output regressional values, right? Whereas liquid neural networks can work with that, and it's pretty lightweight, and it can, it can just take inputs, and it's not static. The weights are not static. It can dynamically change on the go. So is there any reason why your team hasn't explored those ideas, or is it something that?
Yeah, I mean, I'm relatively familiar with liquid neural networks. For example, I was working with Daniela Ras at MIT during my PhD, and some of the developers. We haven't been exporting them. Well, one, because bandwidth is limited, so that's a very simple reason. But for the other one, so first of all, it depends how you interpret changing in real time, right? And also how much you trust the specific output. So I would say for now, the main reason why we haven't explored them is lack of bandwidth. We'll probably look into them, but with all technologies, there are pros and cons.
There's one question from chat. So actually two questions. So during your AV development, have you encountered the following two cases? So the first case is that instead of full self-driving cars, you use models to assist human driver. And the second case is that have you encountered cases that when humans drive the car, so the model can learn from the human driver?
Well, I mean, in terms of how these models are trained, is mostly through imitation learning. So yes, the driving behaviors are learned through expert trajectories. So these expert trajectories are typically collected through a driving fleet. But something interesting, and this goes beyond autonomous driving, actually in robotics, is tapping into heterogeneous data sources. So today we only talked about expert trajectories, that are gathered, or maybe internet scale pre-training. But there is also stuff in between. Like for example, a lot of cars have a lot of taxis have dash cams. So this is additional information that you could leverage as a sort of in-between internet scale and but not very driving specific and highly accurate videos. But bottom line is that yes, absolutely. These days, but not just for end-to-end models, I would say even for modular models, the decision-making logic is trained to a large extent on based on expert trajectories. So the first one is, do we use this model for in-cockpit use cases? Well, I'll show you an example that is called LADA. So definitely, as we speak, several companies are working at racing toward deploying large language models in the cockpit as a sort of a copilot.
And a follow-up question from the chat that so in your LLM-based driving case, is there any case that the LLM is listening to the human direction? So basically, it's reacting according to the.
No, it's reacting in the sense that, of course, the human provides high-level guidance about where to go. But in general, you don't want to have a more. We're talking about. Even for L2++ L3. You don't really want to have control at a much more granular level, because otherwise, again, it's a question of practicality. It completely invalidates your validation process. You're still operating under some assumptions, right, to validate your system. If at any point in time, for example, the human might decide to override your arbitrator to say, I don't want to give control back to the contingency planner, I want to stick with an end-to-end planner, then your entire validation case will go out of the window. So yeah, in principle, it's possible, but I don't know to what extent it will be interesting for a consumer standpoint, and from a safety standpoint, it will be extremely challenging.
You showed us a diagram where there was a foundation model and then there was a bunch of heads on top of it. So the planning head, is the planning head also a foundation model, or is that some sort of different?
No, an example that I show is not a foundation model. So it's just a simple policy that is trained on trajectory regression. But in principle, it could be. So the parallelized architecture that I showed is just an archetype. In general, I think the even more interesting question is how do we reason about policy structuring? In the sense that so far, I would say the community at large is doing the simplest possible thing. So your policy head is trained on the task of a trajectory regression. But that's not the only thing. And you could do it auto-regressively, maybe you could do it through diffusion and so on. But there are other ways you can do it, right? For example, your policy head might output a value function. and then you do search with respect to the value function. And so this is more in line of this kind of emerging trend of doing more test time optimizations. And this is more generally in control. There is always this oscillation between what, doing everything offline and everything online. It always oscillates. Like, for example, in controls, traditionally was everything online, then it went to everything offline, then with MPC, it went everything online. So and it's also probably what will come next in robotics and autonomous vehicles. So some more sophisticated ways of output, of structuring your policy. Maybe you can predict a tree or trajectory so that you can reason about different contingencies. But for the sake of all the things that I just showed the simplest possible thing.
Some people say that like real world data is always better than the simulated data because simulation requires a lot of computations, and every time you evaluate models, the results may be different. Also, like as you mentioned in the demonstration, there's some artifacts during the simulation. So people say propose non-reactive simulation-based metric like NavSync.
NavSync.
Yeah, I saw you are also on the also list.
Yeah.
So how do you come on their idea that like no simulation, just a real world data?
So I think there are two different things. So one is how do we blend the real world data with simulation data? And the other one is which metrics or KPIs we use for training. So the simplest possible way to train a model is to use so-called open loop KPIs. Essentially, you regress a trajectory, you compare to the one that is being acquired by an expert, you form some distance, and then that provides your loss signal. The problem, though, is that that type of metric does not account for the fact that your policy in the real world is going to drive its own predictions. So it does not account for potential closed loop effects that might actually lead the vehicle away from an expert trajectory, thereby causing distribution shift and very poor performance. So how do you give some notion of closed loop performance to a metric that is used for training? So that's a so-called open loop to closed loop gap in terms of metrics that are used both for training and for evaluating a given model. So what the work that we refer to NavSim try to do is to introduce a score referred to as a PDM that is still an open loop metric, but that with some clever tricks endows the metric with some flavor of a closed loop. So basically, it aligns much better with closed loop. This is a very severe problem. You might have models that are awesome open loop, then you deploy them on a car, they're garbage because they nearly run out of distribution and then become erratic. So that's one. So in general, I do think that closed loop simulation ultimately will give an edge in terms of training better policies. But you're right, there might be something in open loop that's more correlated with closed loop, much faster, much lighter weight, and still highly performant. In terms of simulation and real data, I mean, that's a debate that every robotics company and every AV company has. It's true that simulation is expensive, but certainly not as expensive as driving a real fleet of vehicles, and allows you to generate all sorts of scenarios and so on and so forth. I think we're getting much closer in terms of using a simulation, particularly for synthetic data generation and also for testing. We are not there, and of course, we will mix it with real data. We are not there yet at the level of using simulator for safety validation. So this is something oftentimes a bit overlooked in academic literature. People say, oh, I have an awesome simulator, then I can use it for safety. You cannot, because then you will need to validate the simulator to basically show the KPIs that you get out of the simulator are actually trustworthy and can be interpreted the same way as you would have on the real vehicles. Actually, we're working on a couple of papers that probably will be published in a couple of months on the topic of how you validate simulators so that you can also use simulators for safety.
Thank you.
Maybe last question, any advice on how to build systems for autonomous driving that can generalize between different treatments? Have system that can drive really well in Europe and Asia and so on and so forth.
Yeah, so I don't think there is a silver bullet here. As I show, I think foundation models get us a little bit there, but there might algorithms that can adapt much more gracefully in the sense that I mentioned my work on the meta learning, but other methodologies to be trained explicitly in a way that can adapt much more efficiently to new data distributions. But it's not just algorithms. For example, you can be a bit more clever with data. So that's one example where dashcam videos could be useful. They are more informative than internet scale videos because they're specific to driving, and they can be acquired much more cheaply. So I think it's going to be a combination of algorithms that more intentionally are designed to adapt in few shots, and there are a number of different ways to do so. Leveraging foundation models to imbue this kind of generalist experience into the models, and being a little bit more flexible in terms of the data sources that are used as part of the training. That said, you need to have some, I like to give this example, and this is a tip for you if you go to Italy. So if you go to Italy, I'm originally from Italy, as probably you can tell from my accent, so if you go to the north, if someone blinks at you, is a kind sign. It means that you can cross in front of them. If you go to the south, if someone blinks at you, that is an aggressive sign. It means, don't you dare to cross in front of me because I'm not going to slow down. And if you do, we're going to crash. So sure, you can have dashcam videos. Sure, you can have meta-learning algorithms. Still, I would trust the system that has some field data from both the south of Italy. And we're talking about a country that is 1,000 kilometers long. So it's not that, it's very long and very thin.